Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to predict if a mixture of two solutions containing two or more different ionic compounds will form a precipitate. And so in this diagram that I've drawn, if we take a solution of AB that's colored yellow, and if we take some amount of solution CD, which is colored in blue, and if we poured them into the same container, whether it be a beaker or Erlenmeyer flask, the list continues, we're going to assess whether or not the combination of those two solutions will form a precipitate. And the precipitate that I just drew is that squiggly line. And so you guys have already explored this concept once before in the first semester of general chemistry. When you guys were learning how to balance chemical equations, you guys talked about like double displacement reactions, and once you've learned how to perform a double displacement reaction, you guys should have learned how to predict the products. And so once you've learned how to predict the products, then you assess each substance, whether they're a reactant or a product, and use the solubility rules to assess whether or not it's going to be aqueous, meaning it's going to be soluble in solution, or if it's going to be insoluble by designating the precipitate with the physical state of matter solid, or lowercase s. And so what we're going to do is we're going to build upon that knowledge from the first semester of general chemistry. And we're going to look at it in a different perspective using Qsp. So let's go ahead and start. So to predict whether or not a precipitate will form, the solution, somehow we have to determine that the solution is supersaturated with the ions responsible for forming that precipitate. And so, for example, if you have a supersaturated solution of ions that are spectator ions, then, even though it's supersaturated, those are spectator ions, so no precipitate will form. And so the idea of supersaturated must be relevant to the ions that is responsible to form that precipitate. Hence the need for you guys to be very familiar with your solubility rules. And so on paper, one way to assess whether or not a solution is saturated or supersaturated or unsaturated is comparing its Qsp value to that of another value. And so in the first lecture video for this chapter, I mentioned that Qsp, part of the definition of Qsp, is that it is representing a saturated solution. And so Qsp becomes our reference point to determine if reference point. So Qsp becomes our reference point to determine if a solution is saturated, supersaturated, or unsaturated. And if we want to assess whether or not a solution is supersaturated or unsaturated, we need to compare the value of Qsp to another value. And what we're going to compare it to is Qsp. And so to determine if the solution is supersaturated, saturated, or unsaturated, we're going to compare Qsp and Ksp. And so much like the equilibrium chapter that we discussed a few chapters ago, Q, this idea of Q, it represents the ratio, the relative ratio of reactants and products at any point in time. It could be at equilibrium, it could be before equilibrium, it could be way, way after equilibrium has been reached. And we're going to apply that same idea to determine whether or not something is saturated or supersaturated. And so, or unsaturated. So Ksp becomes a reference point, and it's always representing a saturated solution. And so if Qsp, which is the ion product, is greater, so if Qsp is greater than Ksp, that means we have a higher product of our ions than the product at saturation. And so when Qsp is greater than Ksp, then you can conclude that the solution is supersaturated with the ions that's responsible to form the precipitate. And so therefore, the precipitate will form. Okay. And remember, it's the ions that is supposed to produce that precipitate anyways. And so if you guys have a supersaturated solution of your spectator ions, then for the scope of what we're trying to learn in this section, it won't form and precipitate. And so let's go ahead and look at the other different combinations. So if Qsp is equal to Ksp, then you are at saturation. So your solution is just saturated. And if your Qsp is less than the Ksp, then the solution is unsaturated. And so for these two scenarios, when Qsp is equal to Ksp and Qsp is less than Ksp, no precipitate will form. Okay. So we only really have one combination, one possibility that will allow our ions to come together to form a precipitate. And that is when Qsp is greater than Ksp. Okay. All right, so this is just like the background for what we're going to be doing. Let's go ahead and apply this background information into a word problem. And we're going to see how we can possibly assess Qsp. So in this problem, we have a student who has 2 water samples. And one water sample contains 1.0 times 10 to the negative 9 moles of calcium. And the other water sample contains 2.0 times 10 to the negative 7 moles of phosphate ions. If the student combines both samples to produce a total volume of 1 liter, will a precipitate of calcium and phosphate form? Okay. And so the first thing that we need to do is we need to look up the Ksp value for the precipitate of calcium and phosphate. So will a precipitate of calcium and phosphate form? Actually, the first thing that we need to write is what the chemical formula looks like for calcium and phosphate. And so since calcium has a fixed charge of +2 and phosphate has a fixed charge of -3, if you crisscross the value of those charges or balance the charges, however you guys learned it in the first semester of general chemistry, you guys will get 3 calciums for every 2 phosphates. And if you guys look at this substance in your solubility rules, phosphates are naturally insoluble, and calcium is not an exception to its solubility. And so we can go ahead and predict that calcium phosphate is going to be our precipitate, could be our precipitate. So we're going to ask ourselves, will a precipitate form? Under the condition that we have this number of moles of calcium and this number of moles of phosphate ions. So now that we've determined the chemical formula, we're going to have to look up the Qsp. And so the Qsp can be determined from a reference chart, and I'll go ahead and make sure to post a document that summarizes the Qsp for most of these slightly soluble, mostly insoluble substances. And so it turns out that the Qsp for calcium phosphate is 2.07 times 10 to the negative 33. Okay. And so this is the Qsp at 25 degrees Celsius. And so remember, the Qsp is going to change depending on the temperature. And so what we're going to do is we are going to assess whether or not this number of moles of calcium, this number of moles of phosphate ions is going to be enough to create a precipitate. And the only way for a precipitate to form is to determine whether or not Qsp is greater than Ksp. And so the value of the Qsp is already found. I mean, we just looked it up. So the Qsp is going to be 2.07 times 10 to the negative 33. Okay. So remember, your K values are unitless. And so to figure out your Qsp, we need to determine the ion product. And so, excuse me. So if you guys have, how do I say this? So this is our precipitate, right? This is our slightly soluble, mostly insoluble substance. And so to determine Qsp, we need to determine the mass action expression for it. And so to determine the mass action expression for it, we have to write a balanced chemical equation, write an ice table, and then plug everything in so that we can get the mass action expression for Qsp. And so here we have calcium phosphate. And we know that it's going to produce 3 moles of calcium for every 2 moles of phosphate, when a small fraction of that slightly soluble, mostly insoluble substance dissociates. Okay. All right, and so when you guys are trying to figure out the Qsp, the ion product, what you guys want to do is determine the mass action expression. And so I apologize, I mentioned a little bit earlier, you guys have to develop an ice table, but whenever you guys are calculating Qsps or any Qs, no ice table is required. I think at that moment in time, I was just on autopilot. My brain was just on autopilot. And so to determine the value for the QSP, all you need to do is write a mass action expression based on the ion product. And so in this case, the QSP is equal to the product of calcium and phosphate raised to their coefficient. So we're applying just the definition of QSP. And so notice that this bracket, I'm not saying that we're at equilibrium. And so this is the reason why this is the reason why we don't need to write an ice table. Because for the ice table, we're trying to determine the equilibrium concentration. But Q doesn't necessarily have to be at equilibrium. And so this is the reason why we do not write an ice table for it. We just go straight into the mass action expression. So remember how when we write KSP, or I'm sorry, yeah, KSP, KA, KB, whatever, we put like an EQ over here to remind us that these concentrations are at equilibrium. And so for QSP, it's not. It's at any point in time. And so the only thing that we need to do is build our mass action expression, make sure that the coefficient is raised to the power for that specific ion. And if you guys recall, the bracket represents molarity. And so all we have to do is plug in the molar concentration of calcium, raise it to the third power, and multiply that by the concentration, by the molar concentration of phosphate, and raise that to the second power. So once we figure out the molar concentrations of calcium phosphate and plug it in, we can just plug everything into our calculator and figure out what QSP is. All right, so if I look at the problem, it didn't give me molar concentrations, it gave me moles. And so I have that many moles of calcium and 2.0 times 10 to the negative 7 moles of phosphate. And so if you read on in the problem, it says that we have a total volume of 1 liter. Okay, so we're mixing these two substances so that the total volume is 1 liter. And so we can go ahead and take this value, and just divide it by 1 liter, and that will just get us molarity. So 1.0 times 10 to the negative 9 divided by 1 is the same value. Same goes for 2.0 times 10 to the negative 7. And so in this very simple problem, we're simply taking, 1.09 or 1.0 times 10 to the negative 9 molar concentration, raise that to the third power, and then times this by 2.0 times 10 to the negative 7 molar concentration raised to the second power. And so now that I've filled in my values, I'm just going to go ahead and plug this into the calculator here. So just give me a second. So 1.0 times 10 to the negative 9. I'm going to raise that to the third power. And then I'm going to multiply that by 2.0 times 10 to the negative 7. And I'm going to go ahead and raise that to the second power. I'm going to add another parentheses here. Give me a second. Okay. And so it looks like the QSP is equal to 4.0 times 10 to the negative 41. And so I will not add in molarity because remember QSP is a constant. It's a ratio of the forward and reverse reaction. And so therefore it's going to be unitless. I just placed molarity here just to be consistent that I'm plugging in the concentration. But at the very end in your answer, it should be unitless. Okay, and so now that I've figured out my QSP, I'm going to go ahead and compare that to KSP. So if 4.0 times 10 to the negative 41, that's going to be my QSP. And my KSP was 2.07 times 10 to the negative 33. So 2.07 times 10 to the negative 33. And that's my KSP. All right, so now that I've tabulated my values, I'm going to compare them. So which one's greater? So if you said KSP, then you're correct. In this scenario, negative 33 is closer to 0 than negative 41. So QSP is less than KSP. So is this solution saturated, supersaturated, or unsaturated? And so this solution is unsaturated. So I'm going to scroll up. So if QSP is less than KSP, then your solution is unsaturated. All right. And so since your QSP is unsaturated, this is telling us that we don't have enough molar concentration of the calcium and the phosphate for it to form a precipitate in the solution. And so this is something different. This is a little bit different than what you guys are used to doing in the first semester of general chemistry. In the first semester of general chemistry, you guys just looked at a chemical formula and you predicted whether or not it's soluble or insoluble. And so just because your solubility rules says that it's insoluble or soluble, it doesn't mean it's always true. You have to consider the concentration. You have to think about the temperature, the pressure, all of these external factors that really truly reflects the solubility for these slightly soluble, mostly insoluble compounds. And so we're using our K's and Q's to assess whether or not our solution is going to to assess whether or not these ions that's supposed to form a precipitate will actually form a precipitate given the actual amounts present in the solution. Okay? And in this scenario, since it's unsaturated, since QSP is less than KSP, the precipitate of calcium phosphate will not occur. Okay? And so before I move on, I only did this so that I can determine the number that's going to be in the exponent so that I can calculate QSP. Okay? And so one of the common mistakes that I see that students make is them not writing the correct chemical equation. And so we're always assuming for this chapter that the slightly soluble substance is going to be our reactant and our ions will always be our product. So just make a mental note of that. All right, so let's go ahead and take a look at another example. So here, if a student mixed 25 milliliters of 0.035 molar of silver nitrate with 15 milliliters of 0.015 molar of sodium chromate, will a precipitate form? Okay. So this problem is just a little bit, it's not too complex, but it does involve a little bit more steps. And so the first thing that we need to do is translate what this means. And so silver nitrate is Ag with a positive charge, NO3, that's nitrate. Notice it's +1, -1. And so the substance is simply AgNO3. And so here we have sodium chromate. I know that sodium is +1. Chromate is CrO4 with a -2 charge. And those are polyatomic ions that you guys should have memorized from first semester of general chemistry. And so I'm going to balance my charges. So I have +1, -2. So that means I need 2 sodiums for every 1 chromate. Okay. All right. And so now that I have my reactants, so these are the substances that is going to come together and produce my products, I'm going to write a rough chemical equation. And I don't need to balance this one all the way through, and you'll see why in just a second. And so here I have silver nitrate reacting with sodium chromate. And it's going to produce, notice that I have 2 cations, so this is a double displacement reaction. And so for the double displacement reaction to occur, I'm going to switch the position of my ions. But when you guys switch the position, you guys are not keeping the subscript. You guys need to create a new chemical equation. And so you will have to think about how the charges, the original charges, is going to affect your new products. And so typically I just like to write this as, so I'm just going to go ahead and show my work here. So I'm going to go ahead and write my reactants in their ionic form. So I have silver plus, nitrate with a negative charge. Here I have sodium with a positive charge and chromate with my -2 charge. And sometimes writing it in their ionic form will help us create our product. Okay. It'll help us create the chemical formula correctly for our products. And so here I have Na is now going to be paired up with NO3. And we have silver that's going to be paired up with chromate. Okay. And so now that we have our chemical equation in their kind of ionic form, we need to write a balanced chemical formula. And so here I have +1, -1, so I don't really need to write a subscript. And so this is just a 1-to-1 ratio between silver and nitrate. Now, if you guys are looking at the charges, we have a +1, here we have a -2. You guys combine this together and you get Na2CrO4. And for your products, notice it's +1, -1. And so when you're balancing those charges, you get NaNO3. Here you have +1, -2, so you need 2 silvers for every 1 chromate. Okay. And so if this was first semester of general chemistry, you guys would need to balance the entire chemical equation with coefficients. However, when you get up to this point, when you guys have predicted your products, remember what we're trying to do here. We're trying to determine whether or not a precipitate will form. And so which of these 2 products will be a precipitate, or could be a precipitate, according to the solubility rules? Okay, and so let's go ahead and apply our solubility rules. So sodium and nitrate, if you look at their solubility rules, they're soluble always and always. And so this is going to be aqueous. So therefore, this cannot be the identity of our precipitate. If you guys look at your solubility rules, chromates, CrO4, are typically insoluble. And so I wrote a list of your solubility rules on an earlier lecture video. So please make sure you guys go back to that lecture video, take a screenshot or write it down, just so you guys have it for reference. And so chromate is usually insoluble unless it's partnered up with a group 1A element or ammonium. And silver is not a group 1A element, nor is it ammonium. So therefore, this substance is going to be our precipitate. Okay. And so now that we've identified the identity of our precipitate, now we have to determine if precipitate actually forms, right? So right now we've just identified what the identity of the precipitate could be or is, and now we have to think about how the concentrations and how the volume will determine whether or not a precipitate will form. And to do that, we need to compare Qsp and Ksp. And so the problem didn't really give us, the problem didn't give us Ksp. So Ksp, and this is something that we're going to have to look up, or you guys just have to go to this reference page that I'll post on Canvas and look up the values. But the Ksp for silver chromate is going to be 1.1 times 10 to the negative 12. So this is a value that you don't need to calculate, you just need to look up. So from reference. And so what you have to calculate is Qsp. And now that we've determined that our substance is silver chromate, we're going to go ahead and write a mass action expression to reflect that of silver chromate. And so therefore we're going to take our silver chromate and we're going to write an equation to represent the production of its ions. And notice how there's 2 silvers for every 1 chromate. So we got to make sure that's represented correctly. In our equation. Okay. And so since Qsp is not at equilibrium, then this tells us that we do not need an ice table. And so to determine the value of determine the mass action expression of Qsp, we're just going to take the product of the ions. That's why it's called the ion product. So if you guys look at the definition of Qsp, it's the ion product. So it's the product of the ions. And so we're going to take the concentration of silver and we're going to raise it to the 2nd power. Okay, because it has a coefficient of 2. And then we're going to multiply that by the concentration of chromate raised to the 1st power because its coefficient is 1. And so I'm going to take a step back here. It's super, super, super important that you guys are able to write the chemical formula correctly for any substance. In this scenario, if you guys did not write the correct chemical formula, then your mass action expression, the exponents in your mass action expression for QSP will be wrong. And if these exponents are wrong, then your QSP value will also be wrong. And if your QSP value is wrong, then perhaps you would have gotten an answer that is incorrect. I mean, depending on the values, you might get the answer correct just by coincidence, but the process is wrong. And so just please, please, please make sure you guys review how to write your chemical equations, how to balance chemical formulas. And once you guys have written or predicted your products, you don't really need to balance this whole entire chemical equation. You guys just need to focus on the products and determine which one is going to be insoluble in solution based on solubility rules. So all of these concepts from Chem 110 or first semester of general chemistry, they're stacking for this chapter. Now, to determine the equilibrium concentrations, we need to determine what the concentration of silver is and what the concentration of chromate is. And so here it says that the concentration of silver nitrate is 0.035 and the concentration of sodium chromate is 0.015 molar. However, you guys cannot use these concentrations. Why? Let's think about it. Let's read the problem. You guys have 21 there. You guys are putting 25 mils of this concentration, and you're mixing it with 15 mils of this concentration. Let me take those circles away real quick. Let me just do it through highlights. And so you guys are taking 25 mils of this concentration of silver nitrate, and then you guys are taking 15 mils of this concentration of sodium chromate, and you're putting them in one container. Remember that molarity is volume dependent. It depends on the volume. And so your molarity will always change if you increase or decrease the volume of your solution. And so before you can even calculate before you can even plug the concentrations, you need to recalculate the concentration of silver nitrate, and you need to recalculate the concentration of sodium chromate. Okay. So let's go ahead and do that. So we're simply going to take, we're going to be using our dilution equation. And so if we want to figure out the new concentration of silver, we're going to have to use our dilution equation. And this new concentration is representative of M2. Okay, so M2 is the concentration that we want to figure out. Now, the initial volume for silver nitrate is 25 mils. And you guys don't need to convert milliliters to liters when you're using the dilution equation. So I have 25.0 mils. And then we're going to, and then we're going to multiply that by the original concentration, which is 0.035. And then now we're going to go ahead and figure out what V2 is. So V2 is the total volume of the new solution. And so the total volume is simply the sum of these two. So 25 plus 15, that's going to be 40. And so we're going to solve M2 by multiplying those two values and dividing it by 40. So 0.035 times this by 25 and divide this by 40 mils. And the concentration that I get is going to be 0.021875 molar. So looking at our sig figs, I have, looks like 2 sig figs is my least if I'm looking at my original values. And so I'm going to just keep the first 2 significant digits that I see. So the concentration of, the new concentration of my silver is 0.022 molar. Okay. All right. And so what I'm going to do is place that concentration into, that new concentration into where it's found in Qsp. And so here, the concentration of silver is going to be 0.022 molar squared. Okay. And so to figure out the new concentration of chromate, we're gonna go ahead and apply the same concept, apply the same formula. So to determine the new concentration of chromate, we're going to have to use M1V1 is equal to M2V2, where M1 represents the original concentration, which in this case is 0.015. So 0.015 molar. And then I'm going to multiply this by the original volume, which is 15 mils. And then I'm going to solve for M2, and the total volume is the same as the same as the previous one. It's just the sum of 25 and 15, which is going to give me 40. And so I'm going to solve for M2 by dividing 40 to the other side. And so I'm going to go ahead and take 0.015, multiply that by 15. That's going to give me 0.225. And if I divide that by 40, that's going to give me so 1, 2, 3, 6, 2, 5. So I get 0.005625 molar. And since my least number of sig figs is 2, I'm just going to keep my first 2 sig figs. So it's 0.0056 molar. And that is going to be the value of M2, which represents the new concentration of chromate. All right. And I'm going to go ahead and plug that value into here. So 0.0056 to the first power. Now that I have my new concentration, I'm simply going to raise each value to their power as indicated in the equation and multiply them together. So 0.022 squared, that's going to give me 4.84 times 10 to the negative 4 times that by 0.0056. And then that's going to give me a Qsp value of 2.7 times 10 to the negative 6. And once again, remember that Qsp is unitless. And so now that I have the value for Qsp, I'm going to go ahead and compare that to my reference. And so my Ksp is equal to 1.11, or I'm sorry, 1.1 times 10 to the negative 12. And so now that we have Qsp and Ksp, how will we determine if this solution will precipitate or not? So we're going to have to look at the value that's a lot larger. And which value is larger? Okay, so if you said Qsp is larger than Ksp, then you guys are correct. And so times 10 to the negative 6 is closer to 0, so therefore it's a larger number compared to negative 12. And so Qsp is greater than Ksp. And if you look at the very, I'm going to scroll up here just so you guys can see it. And so if you look at these notes, if Qsp is greater than Ksp, then that tells you that the ions responsible to form that precipitate is supersaturated. There's an overabundance of them such that a precipitate will form. And so precipitate will form. Okay. All right, so that's pretty much it for this concept. There's several take-home message here that you guys have to be aware of, and that's really highlighted by the second example. There's a lot of like fundamental concepts that you guys hopefully have mastered or familiar enough that you won't have to go deep into your general chemistry, your first semester general chemistry notes. And if you have to, that's okay. And so first and foremost, in this first step, we have to determine what substance will be our precipitate. And so silver nitrate and sodium chromate are our reactants. And so therefore we have to predict the products. And we have to make sure that we're writing the correct chemical formula for our products. And to do that, I encourage you guys to list out your substances with their charge before you do a double displacement reaction. Okay? And so once you guys have listed out your charges for your reactants, then you can go ahead and switch the position of the cation to reflect a double displacement, and then just write the results, still with their charges. And then after you guys have done this, then you guys are going to balance the charges to create a correct chemical formula. And then once you guys have created your correct chemical formula, you guys need to look up the solubility rules for each of your product to determine which of those two will be the identity of the precipitate. Once you have figured out the identity of the precipitate, you guys then need to use a reference sheet if it's not given to you in the problem, and you need to look up its Qsp. Okay. And so once you guys have determined the Qsp for this specific product from the reference chart, then you want to ask yourself, well, is Qsp greater or less than Ksp? And to do this, you guys need to figure out the mass action expression for Qsp. To do that, you need to take your precipitate, your potential precipitate, this product, and you need to write the reverse reaction, so to speak, so that you can get the coefficients of those ions. And those coefficients are going to, represent the exponent in your mass action expression for Qsp. So once you guys have your mass action expression for Qsp, then you need to determine the concentration of silver and the concentration of chromate in this scenario. And to do that, if you guys if the problem is describing that you're mixing two solutions together with a certain concentration, you guys need to recalculate the new concentration using the M1V1 equals to M2V2, the dilution equation. Once you solve for M2, you guys are going to plug that into the substance inside your Qsp equation, and you're going to do it again for the other ion. And once you get your new concentrations after you've mixed those two solutions together, then you can go ahead and plug everything into your calculator to determine the value for Qsp. And then you guys are going to compare Qsp and Ksp, and if it's greater than Ksp, if Qsp is greater than Ksp, then a precipitate will form. The silver chromate precipitate will form in this example. The identity of the substance will change in future problems. And if it's less than if Qsp is less than Ksp, or if Qsp is equal to Ksp, then your precipitate will not form. Okay. So on Canvas, you guys have several worksheets. One of them will be from lab, and it'll help reinforce this concept. All right. So that's pretty much it for today's, for this lecture video. The last lecture video that we're going to look at is going to be titled Simultaneous Equilibria, or let's just leave it like that. So we're going to look at simultaneous equilibria, and we're going to perform some calculations on that specific concept, for that specific concept. All right, so I'll catch you guys later. Bye.